Greetings, we are the team Mallocators from IIIT Hyderabad. We will first present the description of the problem. A coordinated distribution of COVID samples within a state can increase the testing throughput while maintaining feasible costs in an already stressed economy. Notably, with the given cost of testing and transportation, the landscape for optimization per day is in the order of tens of crores. We propose a model that can provide fast and high quality solutions. If run for longer, it can obtain provably optimal solution, which in worst case will only be a few lakhs more than the best possible cost. Now, Karnataka has 30 districts, which shall more or less remain static. COVID samples are first stored at a district headquarters and later distributed to labs within the district or outside. Labs are either government or private. Each lab has a fixed per day capacity, above which only the district where the lab exists can overload up to 100 samples with a penalty of rupees 5,000 per sample. With a high penalty of rupees 10,000, each sample can be kept as backlog at the district headquarters to be processed the next day. We thus optimize on a day-to-day basis. While sending samples to external labs, we define a cluster as the group of labs to which we are sending outside. All of the clusters lab have to be pairwise within 40 km. During such a scenario, the Euclidean distance to a centroid of a chosen cluster of labs can be taken as a fair approximation of transportation cost as we are optimizing on a macro level. Moreover, it is assumed samples leave on a single vehicle from the district, so a district sends samples to at max one cluster outside. Now I shall go over the dataset given to us, which represents the infrastructure of 30 districts and 86 labs. It has 5 test files representing 5 consecutive days, varying in per day capacity of labs and the amount of samples that were backlogged the day before. Now we shall analyze the given data points. We notice that Bangalore urban has a group of 34 labs, each within 40 km of the other, thus forming a valid cluster. As you can see in the map, rest of the labs are sparsely distributed with not more than clusters of size 3 or 4 having labs within 40 km. Now, to approach the problem, one would normally start by first filling the public labs inside the district since they are the cheapest. Next, private labs should be filled and then samples should be sent outside. As overloading and backlogging samples is very expensive, this should be avoided as much as possible and only be performed at the latest. We shall refer to this simple and generic method as the baseline algorithm. However, our main method is a mixed integer proving model, which we shall refer to as MIP. Optimal solutions to a MIP can be found using industrial solvers. When sending samples outside, the notion of a centroid naturally emerges once we have chosen which specific external labs which we are sending to. However, we propose a backward formulation. We first prepare clusters of labs in the data and then send samples outside to the cluster centroid. As there can be exponentially many clusters, we select only the important ones to feed to the MIP solver. The details about implementing this technique is available in our report. I will now let Shashwat take over to go through how our solution performs.
Now we'll describe the results our model produces. On the right, you can see the maps of our outputs on two of the test files. Blue dots are labs, red dots district HQs, and lines drawn in between show inter-district transfers. The table shows our scores on the final test data provided. Since we've used an open source solver, our solutions are easily reproducible. The baseline column shows the results of the intuitive algorithm discussed earlier. The total cost for such an allocation is around 13 to 16 crores per day. The MIP 10 minutes column shows our results on running our MIP model for just 10 minutes on a normal laptop. Notice the significant improvement between 1 to 2 crore per day compared to the baseline algorithm. This demonstrates that a model's allocation can save the Karnataka Health Department upwards of 500 crore rupees annually. Running the model for 30 minutes provides further improvements. The best score column is when we run MIP till convergence to optimality, which takes a few hours. You can see that the difference between a 10-minute run and the best score is within 1%. Moreover, with industrial solvers like Groby that have a free academic license, the time required can be cut by 5 to 10 times. The closeness column shows how close we are to a lower bound on the optimal that we computed using approximation techniques. The actual optimal will naturally be worse than the lower bound. Thus, our solution is closer to the optimal than the column indicates, but the given values are what we can prove. Even then, on all test files, our best score is within 0.2%. So the difference of the best score from the optimal is within just rupees 1 to 5 lakh rupees across test data. Since the test files had similar distribution, representing consecutive days on the same infrastructure, we decided to create some exaggerated scenarios to check our algorithm for scalability. We've run these just for 10 minutes and given more time, they're bound to improve significantly. We try the following scenarios. A, an edge case can be to set Bangalore urban, the district with by far the highest capacity, to have 0 samples, redistributing the samples to other districts. All these other districts will now send samples to Bangalore, leading to a lot of inter-district transfers. This makes Bangalore urban a bottlenecked hub. Our model gives within 0.1% of the lower bound in this case. Scenario B, we multiply samples in each district by a random factor between 1 to 2.5 times. This creates congestion, that is scaling up the number of samples to be far more than the manageable capacity. Our model gives almost the optimal allocation possible in this scenario. Scenario C, over time, new labs will get constructed. We simulated this by randomly adding new labs to the map of Karnataka. The resulting output shows that even under a different distribution of labs in the future, our model will continue to provide nearly optimal results. So clearly, our model is robust to a wide variety of scenarios without any special modifications required. This brings us to the end of our presentation. If you're interested in finding out more details about our approach, you can check out our repository, which has both a technical report and open source implementation. It was a pleasure working on this interesting problem. We hope our solution can help optimize the nation's COVID efforts in whatever way possible.